Welcome back everyone, and in today's video we're going to do some more math heavy stuff. We're going to build our first constraint, and our first constraint we're going to build is a cone constraint. A cone constraint allows us to limit the amount of movement based on like a cone shape. It kind of helps you control. You'll see how it kind of looks like in the very end. One of the biggest issues with finding information about constraints is that there's not a lot of information about constraints, especially how to limit rotation of a Quaternion. A lot of the only things I found is people kind of using the Euler to control how much you control rotation. But the problem is I don't use Euler because I'm trying to avoid any chance of having gimbal lock. So I don't want. Since I'm not using Euler to control Quaternions, I wanted to find a very Quaternion only solution, and they really couldn't find one except for an old GDC Vault video by Gino van de Bergen. Even though he doesn't fully understand Quaternion math, he still is able to kind of still do it. Add limitations to rotation, and then have them snap back. Now the problem is I don't even understand what he did, to be honest. He doesn't understand Quaternion math, but he's still able to do it. But the math he did, I can't understand. But it's definitely worth a watch to kind of get a primer of what you're going to get into if this is the approach. Is this where you want to go? The beautiful thing, he does have all his source code online. He calls it the Motion Toolkit. And if you go to joint limits, here you'll find the codes, everything written C++. So the samples are very, very simple. Like apparently the way you apply it is very simple. Problem is, the way I'm going to show you today is very hard because the only way I can figure out how to do it on my own. At some point, I might fully take apart his source code and then reapply it in JavaScript and then have these working right. Because he has a lot of the joints working. He's got the ellipse joint limit, that's kind of, or the swing twist. I think that might be an Euler. Not an Euler, the cone one. The ellipse, I think, is also no. The ellipse, I think, is no. The cylinder one is the one I'm thinking about. That's circular rotation. So yeah, he has a couple of joints, and overall, if you look at the code, it doesn't look too insanely difficult. Like I said, he does a really good job of creating something, and it's open source. And I'll eventually try to port this over. But like I said, I want to try to do this and understand it. The only other sample I found, I'll put this link online in the description below, especially with the video, so you guys can watch his presentation. The only other example I found was here, and even this guy's math is a little off. And on top of that, there's parts of his code that's missing. So even though he kind of explains it, like this helped me figure out a way to do it myself. And the whole premise of it is that you try to turn 3D into 2D. And that's what he does. So he does an ellipse. Today I'm just going to deal with the circle because it's a lot easier to deal with. But overall, my approach today allows me to do other constraints as well. I haven't tried coding them yet, but now I have ideas how to do a hinge constraint, a ball constraint, a couple. I think that's about it, really. Those are the main constraints that you want to do for an armature. So yeah, he has a source code. I think his math is still probably easier than mine's. Like I said, even though he converted everything to 2D, and he's doing a lot of the math in 2D and they're trying to translate it back into 3D for rotations. Again, I don't know what he uses for rotations. I don't know if he even uses Quaternions. I don't think he uses Quaternions. So he might be actually just be using Euler, which again is, like I said, I might be wrong because I don't think there's any mentions at all of Quaternions in here. So yeah, he's not using Quaternions. I don't think so. All right. So, but like I said, I'm using Quaternion. So, but I'm using this concept of converting everything to 2D, and I managed to come up with a solution to apply these ideas in 2D, and to not only limit the rotation of a Quaternion, to snap it right back into its bare limit. So one of the first things I need to do is determine an axis, because the joint can exist in any axis. So I need to know its forward, its left, and its up direction. And I need to basically paint a plane, a circle plane. So that becomes my 3D thing. So my forward will become the center point of my circle. So I end up creating the circle, and my forward direction is my center. And my left and right helps me determine the directions of, like, the radius and things like that of my circle. Ideally, I can probably use these to maybe create an oval shape as well. But I haven't done that yet. I don't know if I need an oval shape. I'm probably gonna stick with circle for. But if I need an oval one, I can probably just reapply this, because, like I said, I know the up and down direction, the up and down and left and right directions, so I can resize everything and then use a different equation to kind of draw the circle. Because I do have that plane eclipse function I showed you, I think in the previous video or 2 videos ago. I don't remember at this point. So that's good. So that's the idea. We're going to first define an axis, and then to figure out all the directions once we know its 4 directions. Now here's the kicker. Quaternions doesn't necessarily have a direction. It's an axis of rotation plus how much to rotate, and the angle of rotation. So it's an axis plus rotation. So it doesn't have a direction. There's no forward direction really in Quaternions. So a simple solution. So a simple solution is for me to how I figured this out, how to convert this into 2D kind of, basically 3D to 2D. I need to figure out the forward direction. If there's no rotation, and if I use the forward direction, which would be 0, 1, that's my forward direction. And if my rotation is no rotation at all, then forward will be this. So at this point, I know rotation is. So I need to apply my rotation to the forward vector. So once I apply rotation to my forward vector, I then know basically the direction that the rotation is kind of pointing to, essentially. So I'm creating this illusion of direction based on rotation, which I guess there is direction, but like Quaternions itself, I don't believe have a direction. You can derive direction from it. Like that's what I'm doing. I'm deriving a direction. So if I rotate the forward direction of the forward unit vector, I can rotate it, and at that point I have a new forward direction. So that will be my z-axis. From there, I can use the cross products to define my y-axis and my x-axis, my left and my ups. All right. So once I have my forward direction and an axis, that's what I have here so far. So I have an axis. So like I said, I just rotated. I have a Quaternion. And this is where the point is, and I figured everything else out. So blue and red, it's just cross products from using that new forward direction. Now I need to figure out this, right? I need to figure out the cone. So the cone, and I need to figure out the radius of the cone. So I based that on So if we start thinking this more of in a 2D world, now I have, like, let's say that's my forward direction, and I want to limit my rotation by a certain amount. Let's say I want to limit it by 45 degrees. So 45 degrees is this way. But also 45 degrees technically can be this way as well. It doesn't really matter, right? 45 or negative 45. So that's my forward vector, and I need to calculate 45 degrees from it. So if that's my forward vector, I'm going to use my left vector as a comparison. So using these two vectors, I'm able to then get the 45 degree angle between here and here. So if this is 90 degrees, if I need 45 degrees, I can then use this along with this to kind of help me go in that direction, 45 degrees. I can also probably lerp as well. I don't remember if I use a lerp. I haven't touched this function in like 2 days. And of course I didn't look before I make this video. But another probably solution is like once I have these two things, you can lerp. If you want to convert this, like might want to do this in the future. Convert this from saying angles. I want to just say like a number between 0 and 1, and 0.5 will give me 45 degrees, and I can just lerp 0.5 between here and here, which gives me a point here, and that creates my vector. So once I have my vector, I need to project this. And if you were here when I was doing raycasting, we did a lot of projection. So we're going to project everything to a plane. So our plane exists here. So technically this is our plane as well, but I'm putting the plane here. So I'm going to project it out. So I need to probably go a little bit further. So if the point is here, I need to project it to this point. So once I have a point here, and I have my point here, because this is my unit vector, this is my forward direction, I just need to find out what is the length between here and here. And the length between here is my radius, and that will define the circle in 3D space. And this is that gray line right there. I think this is about 25 degrees between green and red. And like I said, I projected it onto the plane. So everything's kind of a nice straight line. So everything's on the exact same plane. I projected it. And by getting the distance, I can create the radius. So now I defined a cone in the same direction that essentially the Quaternion is rotating to. Now, this black line is another Quaternion, and I'm rotating a forward vector as well, so I know where that one is going. So it's going in that direction. So at this point, what I can do is project this line as well to this plane. Find where this line exists on this plane. Now, since it keeps going, it's going to be over here. So once I project it onto this plane, I can do the exact same thing I did to figure out the radius. Is find what's the distance between here and here. And let me just do it here. I'll show you the code. Don't worry, but I think you need to visually see this before you can look at the code. So, and besides the way I'm describing it, you can probably code it yourself at this point if you're like me at this. So, like I said, I rotated this, and now you can see now it's actually projected because I made the line longer, and now this is the actual point that the second Quaternion that I'm trying to limit exists on this plane. So when I tested the length between here and here, it's like, well, it's too far. It's outside the range. So since it's outside the range, since I already have the length vector, because I calculate the length vector, and then I grab the length of it, and I can use I think I use length squared, so I don't have to waste time using a square root. But yeah, it's so if I know that length from here to here is greater than the length of the radius from the center, then I know it's over the limit. So, and I know that vector length, by normalizing it, I create a unit vector. And that unit vector, I can then just apply the radius to it, just scale it by radius, and that's the new point. So by using that new point, I use that as a look at target and tell the Quaternion, look at this point in space, and it creates the orange line. And now this black line, which was the original Quaternion, has been constrained to this cone space, which has now been transformed into this orange line. And that's essentially how I took everything everything's still in 3D, but still in a 2D world, because I move everything into the 2D plane that I define based on this forward vector, essentially that forward vector, and that axis, that's axis of definition, the define axis. Because for the radius, I know to use this axis or this axis to define all the circles. And that's essentially how you constrain everything. So you have a new rotation. I rotated by 25 degrees on the X, and then I rotated -10. I think if I were to maybe just rotate 0 and rotate a little bit less. And as you see, the orange is gone because it actually is within the range. So I end up just exiting out the function sooner. So this way I know I'm in a range. I don't need to clamp the rotation. So the rotation is within the cone constraint. So if I put it back, now you see all the orange and everything is like, oh no, you got to constrain it. All right. So again, like I said, that's my new rotation. Vector rotation is just the black line that you're seeing initially, and then in here at number 8, I show you this is the orange line after I use the constraint called apply. In here I have two functions. I have two sets. I have my prototype version. The naming convention and everything else is horrible, and my code is very, very long, and I use a lot of bad naming conventions. So I'm not going to go through that one. I'm going to go through the vinyl version, which is a lot more everything. That's like better. So I have, since everything is, since I'm using Quaternions, I don't need to worry about world space or local space for that matter. I can just, rotation, I can use everything at origin, and everything is basically unit vectors. Everything's kind of within the range of unit vectors. So I have I made a function that does a projection based on origin. So I think I might take I think that's the original function I had I guess from ray tracing. From ray tracing, because I don't need to figure out direction and everything else. So I simplify it a little bit. But yeah, like I said, it passes in the ray length, the plane, normal, and vector, and basically the out vector that I want to save it to, and that defines that puts that point, creates a point on that line, but it intersects that plane. So I'm basically using plane intersection. So my first ray intersection video, this is essentially it. So if you really want to understand this better, definitely check out that video. the first ray intersection, intersecting a plane. And this is what we're doing. Another function I have is get look rotation up. I always have to-dos in our videos about having to deal with the up direction. If I do a dot product of, if I'm trying to figure out an axis, the axes, if I'm pointing up and I use a look rotation with up and up kind of counteract each other. So to do that, if I made a function that says check this target. If this target is near 0, and if the x and z are not 0, then just use the up direction, the world up direction, to help determine the axis. Else use the back, because if the direction is exactly up, then I need a new up direction, and I'm using the back direction as the new up, so I can then apply it to the look rotation. So that's what that's for. I've been meaning to do this for like months, if not a year, but finally made a function to deal with that. So like I said, when we build this cone constraint, we need to know the axis of rotation. We need to know exactly where the rotation needs to be limited. So I'd save all these information, and I have the limit angle, the limit radius in square. And this is the vector that allows me to define the cone. It's that limit rad, whatever. So like 45 degrees is that gray line. That's what the limit direction is. It helped me define the base of the cone. Trying to think. So to define an axis, I can do it 2 different ways. I can define it by just putting in a vector target, and I just calculate the axes that way. I don't know if I can say that word correctly. Another way is by just passing in a Quaternion, and then, like I said, I'll just rotate the forward. I rotate the forward to figure out forward, the z-axis to forward, and there you go. So that's how I set an axes, and set limit. I pass in the degrees. I convert it into radians. Then I use the plane circle to figure out the point, because since I already know the axes, I can then use this function to kind of just figure out the point. Then I do that projection, that gray line projected to the plane, and then I can then figure out the radius, and then I save all the values. So first I get length squared, then I do the square root to get the actual length. And then that's it. And all the information for the constraint has then been set. And then we have the apply function. So we pass in the Quaternion, so we transform the forward vector. That's the black line. So we know which direction it's pointing. I project that line onto the plane, so we know where it exists on the plane. And then I get the radius, the length. I call it radius because in the end it becomes the new radius. But this is the vector length between the center of that circle and the new projected point. And I get the length squared. If the length squared is less than or greater than, false. That means we did not apply anything. There's no applying. It's within the constraint. I return true if I applied it. So this way I can do other things if I need to. If I need to limit it, I'm just debugging. I'm just visually debugging everything. Let's see. So since I know the direction to the new point, I just normalize it. I scale it by the radius, and I add the point of the z-axis. So now it's that orange point on the circle. And then I use that projection radius as the point for. I use that as the target, and I figure out what the up direction is. And once I have the up direction and the forward direction that I want, I use the Quaternion look rotation to reset the Quaternion with the new rotation, which then becomes that orange line. And that's essentially it. And let's see. And like I said, you can set the limit to whatever you want. Right now, it's at 25 degrees. So I think you can't go up. I think the limit is 90, but you really can't go too far. So let's say if I do, let's say, a 45-degree angle, a rotation. This is what it visually looks like. But as you can see, the black line doesn't have dots. There's no orange lines because that rotation is within that range of 45 degrees. So that's how you visualize the cone. It's really huge, 45 degrees for me anyway. But yeah, 45, refresh, and there you go. And that thing's just barely in there. It's just right outside the radius of 45 degrees. And yeah, and that's how I managed to approach cone constraints. Next video, I'm going to try to do hinge constraint, which I'm going to follow a lot same things. I mean, basically, you use a lot of the same code, and then just lock everything to the plane. But instead of it being the plane being projected out as a cone, the plane exists at origin, and then the circle will live at origin, and it'll be rotated that way. But yeah, I haven't coded it yet. That's just what's in my head, how to approach it. So, like I said, this can end up working almost the exact same way as for hinge. Then after that, I have the same idea, and then if that works out, then I can do a ball joint, a constraint, which is the hinge constraint without being locked to one plane of access, not being locked to a plane, because that's what the hinge does. It locks you to a plane, and you can only rotate on that plane. So, like I said, I can do a lot of more joints after I figure this out, but yeah, it's not too bad. Like, I don't know how bad this math is. As long as everything's within range, I don't even use a square root. Do I? I don't think so. I don't know. But I am doing a transform, and the transform is kind of complicated. But like I said, you know, this is the basic idea, how I managed to approach it, and it works. But if you want to learn how to do it Quaternion way of it, or like close to Quaternion, this guy, definitely watch his video. I don't think he explains the math that much, really. He just goes through a lot of concepts.
So let's have a...
So yeah, he has some, but
addition.
All this stuff kind of goes over my head. So...
the problem is...
Yeah, so... Whatever. You can watch it, and like I said, he has a source code here from the show, from his talk, and how to do constraints, but keeping everything kind of at the Quaternion level for the most. I think for the most part. But I think it follows a lot of the same kind of ideas. But like I said, these are mathematicians that know what they're doing. So. And like the code looks so much cleaner and neat. They have these super long equations. I have no clue how they got these equations, but whatever. Yeah, and it uses the Newton-Raphson thing. I tried to look that up. It's something I need to learn at some point. But this is, I know in the previous video I talked about the Constraint curve, and there was like a loop trying to find the smallest point on the curve, and that's what this curve, what it's doing is doing this type of approach. It's just you're kind of traversing through the curve to find, I guess, the lowest point. So even though his code is, I guess, looks cleaner, it does have a loop. So there's a lot of looping going on, and I'm not looping. I'm just doing a bunch of vector maths and measuring distances and things like that. So so I don't know which one's better. I'm assuming his is better because he's the professional. He's the mathematician. He's the professional. I will take into account that this is probably 10 times better than whatever I just showed you. And like I said, there you go. But if you really want to learn constraints, there's a solution, and it's something that I guess is easier for you to for people to understand, especially if you don't need to deal with Quaternions. Because in the end, we just use vectors, and then we could just turn that vector direction into a Quaternion and call it a day. And there you go. And that's it. And like I said, I think the maximum you can go with a cone is about 90 degrees, but at that point, it's insane how much. At that point, 90 degrees, you might as well just use a ball joint. So a ball joint probably be a more simplified version of it, so you don't need to limit it. So a cone is a cone, a ball will be something else, and then hinge joints something completely different as well. Yeah, that's it. There you go. That's constraining a Quaternion rotation based on a cone. And you can define the axis of rotation of where you want to go with a Quaternion as well, which I need to for doing armature stuff. So yeah, that's it. I don't know how long this video is. Thing says 31 minutes. I probably don't want to sit there and BS because my throat's done and I need to eat breakfast, and I haven't. It's like 4 or 5 in the afternoon. 4 in the afternoon. I haven't had breakfast yet. So that's it. I'll see you guys in the next video. I'm taking a little bit of time off to do some 3D modeling. And then, yeah, maybe I'm probably going to take a couple of days, then get back to coding. But yeah, I want to do some 3D modeling, and then I'll probably post some cool things on Twitter and stuff like that. So I want to start having some models that we can move around and really use armature on it. So I want to make something for myself. So see you guys in the next video. Please like and subscribe. And yeah, hope you had fun. Hope you learned something. Bye.